Today I'm going to explain you how word embeddings work, a fundamental concept that revolutionized the way that we work with language in the field of artificial intelligence. So if you want to learn how machines interpret the human language, you're at the right place. There are also more complex versions like contextual embeddings or image embeddings, but in this video we're going to lay the foundation with word embeddings. So let's jump right into it. Okay, we now know that embeddings are a crucial aspect of natural language processing for computers to understand human language. For example, to solve tasks like classification, text generation, word clustering, or general semantic similarity. So we need to convert words into numbers. A basic representation would be the one-hot encoding. It is a sparse representation because let's imagine we would have a vocabulary of 10 words. Then we would have 10 vectors with each 9 zeros and 1 1 at the specific position of the word. And therefore sparse, because if you think about it, if you would have a vocabulary with thousands, 10,000s of words, you would have only one per vector and 9,999 zeros. And while this might be very easy to understand and implement, it doesn't capture any semantic relationship between words and doesn't capture any meaning. So here comes the idea of word embeddings. Word embeddings are a dense representation. They're way more compact and have fewer dimensions, but in a manner that captures the semantic relationship between the words. So I'm going to make an example which is really broken down. It's not the exact representation behind the math, but it's really good to paint a picture. So let's say we would have the word dolphin and human. And now think of the embedding as a representation with noun, verb, animal, mammal, and then the vectors would look somewhat like that. A human and dolphin would be somewhat semantically similar because humans are animals, but less animal than a dolphin, you could say. But both are mammals. This is just for an easier understanding. In reality, each row would have some complex mathematical meaning, which the model has evolved in the training. Could be something in the terms of syntactical role, meaning, typical usage, but these are just ideas, so this is just a very simplified version to think about it. And you also would have here a way bigger corpus of words, and typically embeddings would have several hundreds dimensions, which means several hundreds of rows. And the vectors represent the semantic and syntactical relationship between those words in a high dimensional space. And we will see this later. I will show you some graphs. So the embedding representation is learned by training the model on a really great corpus of text. We really break down the principle. It simply means that words in similar contexts should have similar meanings and therefore similar embeddings. Popular methods to learn those embeddings are word-to-vec and GLOVE. And we will talk about word-to-vec here. So word-to-vec is a simple neural network that can be trained in two ways. Continuous bag of words or skipgram. Basically in the continuous bag of words, you would input the context for a word. And here in the middle is the hidden layer where the actual embeddings get calculated. And then the output will be the word that makes sense in the context. And skipgram works the other way. You input a word, then the embeddings are calculated, and it will predict which context makes sense to this word. Okay, let us actually train an example. So we need those requirements, NLTK, Matplotlib, and Plotly to make some graphics later on. Gensim is the library which will have the word-to-vec, and also scikit-learn for one or two things. Okay, from Gensim models, you want to import word-to-vec. We want PCA, Principal Component Analysis. There's actually a lot of math behind it, but to simply think about it, converts a representation with a high number of dimensions into a representation with a small number of dimensions while still preserving the maximum amount of information, so of relationship between the dimensions. So here we define the corpus, which you might see often. A king is a male, a queen is a female, a king is a man that rules a kingdom, a queen is a woman that rules a kingdom. So I just took the pre-processing function from our last tutorial. We'll remove everything that's not a letter. We will lower every word and we will remove the stop words. and also tokenize the sentences. And for that we need regex library and NLTK also. I extended the first two sentences with cat sleeps all day and the dog barks all day. For the clean sentences we're going to map the preprocessing function to the corpus. Here's what it's going to look like. Okay, here we defined the actual model. We will feed it the clean sentences. The vector size is something we have to play around with, but we don't have many words, so just try it with 5. Essentially, the vector size will be the number of columns. So we set SG to 0. SG is skipgram, so we're using continuous bag of words, and we set input size to 3. So it means that for the one word in the middle that will be predicted, it will take one word before it and one word after it, and that's the window size 3. It considers 3 words. You want to predict male, it will look at man and human. You get the idea. So with model point word to vec and then enter a word, we can get the embedding of one word. And here we have the 5 rows as we said before. Let us see the whole embedding matrix. With model point word to vec key to index, we can get all the words in the index, and this is what we want to put into model point word to vec into the brackets. So here's the whole embedding. The dimensions, we have 15 words and 5 rows. And now we want to do the principal component analysis and see what it looks like in a 2-dimensional space. So let's define it. We want to have 2 dimensions. We have to fit and transform the embeddings. And here the fit transform function, the fit trains the PCA model and transform directly transforms the embedding into the 2-dimensional space after the training is done. Now we want to plot it on the pie plot. We define the figure size. Here we want to see a scatter plot. It takes all the elements of the first dimension of the result, and here it takes all the elements of the second dimension. And the first dimension will be on the x-axis and the second dimension on the y-axis. Okay, here's the result. We also want to add the words. That's our result. Let's see if it makes sense. Okay, some things do make sense. Queen and female are near each other. Male and king, woman and man are somewhat similar. And animal and barking. Cat is also near an animal. Okay, let's increase the vector size. It somewhat makes sense. Of course, it's not a perfect representation. Through the principal component analysis, some information got lost and we don't know what the actual representation in the higher dimension would be. Let's look at it in a 3-dimensional space, and then also let's do some interesting math, some similarity analysis with the cosine similarity. We want to use plotly graph objects. And here the PCA again, but with a component size of 3. And we need to install something at first. Just upgrade NB format. And then we also need to restart the Jupyter notebook. And there we have it, a 3-dimensional representation. That's pretty cool, isn't it? Okay, let's go to some math. Let's use the in-grade similarity function, which should be the cosine similarity. Okay, here's a good result. King and male appear together, so therefore they are somewhat similar, and king and female don't appear together, they're dissimilar. The similarity from male to king is almost equal as the dissimilarity of female to king. I think that's really interesting. All those concepts together, it would make sense that the similarity from man to king is equal to the dissimilarity to king to female. Maybe we can do some more interesting stuff. We need the sklearn cosine similarity. Okay, we add man and rules together and check the similarity to queen. It should be less similar than a man and rules to king. And yes, we can see man and rules is dissimilar to queen, but it's very similar to king. Okay, let's quickly look at the math behind of this. We are talking here about the cosine similarity. Here's a formula. We can calculate it by hand. Let's first transform the model into a vector size of 2. Okay, this might be very wrong now, but we're just interested in the math behind it. The similarity now between man and woman is 99%. And we can calculate this by hand. We have here the representation of each word. We just multiply x1 from both vectors and add it to x2 from both vectors, and then we have to normalize it by the multiplied vector length of both vectors. Here we would have the numerator. Ah, there's an error. Okay, now we have it. This video takes way too long, my brain already hurts. So for man, we take x1 to the power of 2, add it to x2 to the power of 2, then we take the root and do the same with woman. Now we just have to divide the results. There we have it, the similarity 99.9%. Okay, that's enough math for today. What can we use these embeddings for? Some examples were text classifications, semantic similarity as you have seen, and word clustering. And these word embeddings are still used because they are so easy and efficient, but it's not that good to capture the meaning within a context. So if I say I left my house or I turned left, it would not understand the differences or the nuances between the same word in different contexts. But we have more modern methods, transformer-based, Elmo, BERT, GPT, which require more computational resources. So I hope you liked it. I encourage you to try it for yourself, especially the math part here is very fun if you play around with the similarities and see the differences when calculating different words. Thank you for watching, hit the like button, hit the subscribe button, and see you in another video.